In this session, we're going to graph systems of linear inequalities in two variables. First, a reminder of a linear inequality. Suppose we have a coordinate plane here, x and y, and let's say that the x-axis is going to represent the number of boys that are going to go on an elementary school field trip, and the y-axis is going to represent the number of girls that are going to go on this field trip. And suppose that we have a bus that seats no more than 25 people, not including the driver or the teacher. Nobody counts them anyway, right? Then it should make sense that the number of boys, x, plus the number of girls, y, is not bigger than 25, right? Is less than or equal to 25. And what we have here is a linear inequality in two variables. We could fit 25 boys in the bus, in which case there would be no girls. We could fit 25 girls in the bus, in which case there would be no boys. Or we could fit, something like, 12 boys and 13 girls in the bus. That would be no problem at all. The bus doesn't have to be full. We could have one boy and two girls. And if we come up with combinations of numbers for boys and girls, what we would find is as long as the number of boys and the number of girls doesn't add up to something that's more than 25, we can fit them in the bus. But we cannot, for instance, put 30 boys in the bus and 5 girls, or 40 boys and 40 girls. Or in other words, there are combinations of boys and girls that are too numerous, right? The number of students altogether cannot exceed 25. And the delineation that cuts off solutions, right, acceptable ordered pairs, from non-acceptable ordered pairs is actually the line x plus y equals 25. Okay, so what we're doing is we're graphing the line x plus y equals 25, which is what I now have on the plane, and then we pick ordered pairs that satisfy the inequality of x plus y is less than or equal to 25. In this particular case, we aren't considering a negative number of boys or a negative number of girls just because of the situation, but with a linear inequality, what you have is a line that cuts the plane into two regions, those being solutions and non-solutions. When we talk about systems of linear inequalities, what we're going to be doing is pairing two or more lines, in this case just two, on the plane and shading their respective solutions, and then any portion that's shaded twice is going to be the solution to the system. Let's dive in. Graph the solution to the system of inequalities, and the system is 4x plus y is less than or equal to 6, 2x minus 5y is less than 10. Our basic outline is graph both lines. In some cases they're going to be dashed, and in some cases they're going to be solid. This is going to be indicated by whether or not we have a strict inequality. And then we're going to pick test points that will determine which side of the line has the solutions, and then shade according to what we get out of the test points. Sometimes folks say, well, you didn't say to shade. We're shading because it's an inequality. Whenever you see inequalities, you should be thinking about shading. This is true on a number line. It's true on the plane. Okay, make sure you have these 3 steps written down. Let's go. Wait, you can rewind it if you need to. Okay, we're going to graph both lines. The first one, 4x plus y is less than or equal to 6. I'll do that in blue. Now I see that because it's less than or equal to, the line will count. And so this is actually going to give us a solid line in our graph. I think it's easiest if we put this in y equals mx plus b form. And so I'm actually going to graph y equals negative 4x plus 6, and then we're going to use test points to figure out which side to shade. So if y equals negative 4x plus 6, then we have a y-intercept of 0, 6, and a slope of negative 4. So down 4 and to the right 1, down 4 and to the right 1, and then we're going to draw a line. And again, the line is solid because it was a non-strict inequality. Now I'm going to graph 2x minus 5y equals 10. Again, remember I'm graphing the line because that's the boundary. But in this case, because it's a strict inequality, just less than, not equal to, it's going to be a dashed line. Because of the numbers in the equation, 2, 5, and 10, I'm going to graph using intercepts. So letting x be 0, I get negative 2 for y. Letting y be 0, I get 5 for x. And I can plot these points and connect them with the dashed line. And there we are, 0, negative 2, 5, 0, connected with a dashed line. Now I need to know which sides of each of these lines to shade. And I do these one at a time. First, the point that I want to use to figure out which side to shade is any point that's not on the line. And since the origin is not on the line, either line in this case, but in particular the blue line, 4x plus y equals 6, I'm going to use 0, 0 in place of x and y, see if I get a true statement. So 0 plus 0, is that less than or equal to 6? The answer is yes. And so as far as that blue line is concerned, I'm shading to the left because that's the side that the origin is on. Remember, the line is the boundary of solutions. Anything on that side is going to be a solution to the inequality. And I encourage you to select some ordered pairs on both sides of the line and see which ones work and which ones don't. You'll see that we have the right shading here. Now I'm going to turn my attention to the red dashed line, 2x minus 5y equals 10. I'm going to again use the origin because that's not on the red dashed line. And we're going to put that into the inequality. We're going to see if 0 minus 0, is that indeed less than 10? And the answer is yes, 0 is less than 10. And so we're going to shade the side of that line that includes the origin. In this case, it's the top. It's above the line. And again, you could select various points on the plane to see that the ones that we have selected are actually the solutions. Now, I said a minute ago that anything that's double shaded is going to be a solution, and so I'm actually reshading the parts that have both red and blue shading. It's starting to look kind of a mess. But then now I'm also going to redraw the blue line, and then we're going to redraw the red boundary, and what we have is the set of solutions. Now sometimes on a test folks aren't sure that it's clear to me. What you can do actually is you can put a little arrow and say it's this part, although that's not necessary if you have made it clear to me. It wasn't actually necessary to shade everywhere else, and so you might just kind of see what the solution is going to end up looking like and just shade the part that has the solution. But ultimately what we have is a bunch of ordered pairs that extends infinitely far that make true statements when we put them into both of the original inequalities. So this is what is meant when I say graph the lines, solid or dashed, use test points, and then shade accordingly. That's what we're going to do in our next example as well. Graph the solution set to the system of inequalities. 3x plus y is greater than negative 5. X plus 2y is less than or equal to 0. And as I said, we're going to graph both lines, solid or dashed appropriately, pick test points, and then shade. Don't forget to shade. So I'd like for you to go ahead and do this on your own. Pause the video and then come back. And so given the numbers for 3x plus y equals negative 5, which is what I'm graphing, seems to me I want to put this in slope-intercept form, so I did. And I didn't do this in the last example, but it is good form to go ahead and label the line. So there it is, 3x plus y equals negative 5. Remember, the line is the boundary It's the actual equation equals -5. The inequality part is in the shading. In red, I'm going to go ahead and take care of x plus 2y is less than or equal to 0. Seems I want to solve for y for this one also. And because this is a non-strict inequality, I went ahead and drew that using a solid line. And now for the blue line, the blue dashed line, I can use the origin as a test point. And we can say, okay, 0 plus 0, is that greater than -5? The answer is yes. So we're going to shade the for the blue line, the part that includes the origin. I'm going to keep that in mind, make a little note to myself, but I'm not actually going to shade it just yet. I want this to be nice and tidy. For the red one, it goes through the origin, and so I don't get to use that point. What I can use is any point that's not on the line, and so I'm actually going to use the point 1, 0. If I put 1 in place of x and 0 in place of y, do I get a true statement? Is 1 plus 0 less than or equal to 0? The answer is no. And so I don't shade the red line on the side that includes the point where the answer was no. I'm going to shade the other side. And so that's going to be, looks like kind of below the line in this case. What we're looking at for the blue line are the points that are to the right of it, or I mean above it. Above is difficult for me to figure out sometimes with these. For the red line, it's the points that are below it. And so what we're looking at is the point where, or the points where the shadings overlap. Now I've lost my equation here, so I'm going to rewrite it. I've drawn now the lines solid and dashed respectively in black, and now I'm shading the solution set to make it clear for one and all that these points in between these two lines are the solution to the system. That's it. Short and sweet.